Hello, this is exam 2 from summer 2019 from MA 303. This was one of Dr. Chen's lectures that he's very kindly given me permission to run through. The syllabus for this class has changed a good bit since this exam was given, and now about half of our exam 2 is Laplace transforms instead of what happens here, where you'll see we have like a 6.4 question, and then 9.1, 9.2, 9.3, 9.4. And then we actually get into partial differential equation territory. We have some heat conduction problems and even a wave equation at the very end. And what I did last night was record the entire thing, but I'm realizing more and more that, this is how our syllabus is this summer for this class is likely how it's going to be in the future. So it's a little silly splitting it up like that. So I'm just going to do the questions that are relevant for the modern midterm 2s. And that begins with this question for 6.4. So question 1, the following equation models a spring mass damper system with a soft spring, and the phase portrait is shown below. If there's no initial velocity, what is the maximum initial displacement that would allow the mass to return to the x is equal to 0 equilibrium? Okay, so what can we do here with this equation that we're given? Because what we would like to do is turn this into a system of two almost linear equations that then we can go analyze for critical points. Oh no, is the dog really going to do this? I hope not, I'm sorry. That we can then analyze for critical points to figure out our answer here. So let's say that x prime is equal to y, and that y prime is equal to, well, something else. Let's figure out what that will be. Let's grab this equation and do some substitutions. So if x prime is equal to y, we'll take this 2x prime and replace it with a plus 2y. What about x double prime? Well, if x prime is equal to y, then y prime, if we just walk back 2 steps, is x double prime. So we can have y prime there in place of that x double prime. Then our x's are still the same, so we have plus 5x minus 5/4 x cubed is equal to 0, or y prime is equal to, all this stuff moved to the other side. So that is minus 2y minus 5x plus 5/4 x cubed. Now if we're looking for critical points, since one of our equations is x prime equals y, in order for us to have a critical point, both x prime and y prime have to evaluate to 0, and the only way that that happens is if y is equal to 0. So y is equal to 0 for all critical points. Now with that in mind, we can go down to our second equation, set y prime equal to 0, set y equal to 0, and we are left with 0 is equal to negative 5x plus 5/4 x cubed. Let's divide an x out of everything. Let's divide a 5 out, add 1 to both sides, multiply both sides by 4, and then we'll see that x is equal to plus or minus 2. And then it's also good to note that since these equations here are homogeneous, that we're going to have x is equal to 0 as another solution. So our full set of critical points is negative 2, 0, 0, 0, and 2, 0. And that's backed up by our phase diagram here. We have, looks like a saddle point here, a saddle point here, and a spiral sink in the center there. And it's good to remember that our x-axis is displacement, and our y-axis is velocity. Okay, so with that in mind, what they're asking is if there is no initial velocity, so that means we're stuck along the x-axis, what is the maximum initial displacement that would allow the mass to return to the x is equal to 0 equilibrium? Well, it looks like that this spiral sink kind of has control for this general area of the graph. Anything that starts in here, and all we really care about is the area right around the axis. Anything that starts in here will get sucked into the origin as time goes on, whereas anything that starts on the other side of either of these saddle points, if we just follow our arrows, will end up off in the middle of nowhere which is not the origin. Because remember, our origin in this phase plane is the point where displacement is 0 and velocity is 0. So that will return us to x is equal to 0 displacement, and it will be in equilibrium because this is a sink point. So it is stable. The mass is going to reach it and not go anywhere once it's there. And since we know that these points now are -2, 0, and 2, 0, the maximum displacement from the origin is obviously 2. Oh my god. There are loud cars driving by. Sorry about that. Okay, question 2. We have a piecewise function here with a period of 2 pi. We're trying to find two coefficients, the a3 and the b5 coefficient of this function's Fourier series. So with these Fourier series, you always have to graph the thing out. The vast majority of the time, if you know how to do the integration, the mistakes that you make will be because you did not, either you did not graph the function correctly and you misunderstood what it was evaluating to, or you put the wrong extensions on it, or you just didn't graph it at all, so you never even really tried understanding what's going on with this function, because often it's easy to overlook what seems like the easiest part of the question, which is just, look, it's -1, 1, and 0. Those are easy little numbers, but if you misinterpret it, you will get the question wrong. So let's take a look. It's our function evaluates to -1 from -pi to 0, 1 from 0 to pi, and it is 0 at the discontinuities. So I'll just draw that in there. This is pi, -pi, -1, and 1. Okay. With that in mind, let's take a look at what's going on here. Is this a special kind of function? Is it either an odd or an even function? Well, an even function is one that if we took the half above. Sorry, I just threw my pencil. Sorry, sorry about that. If we take the half that's above or in the positive x region and we reflect it over the y-axis, so if it was over here, that would be an example of an even function, and I'm pretty sure the way to write that would be that f of t is equal to f of -t. Now, if this was an odd function, what we would expect to see is two reflections. So a reflection over the x-axis first, over the y-axis first, and really doesn't matter which order, and then over the x-axis. And that's exactly what we have here. Our function ends up at -1. It's kind of what they'd say is reflected about the origin, and that is represented with f of t is equal to -f of -t, like so. And since this is an odd function, it will only have a Fourier sine series. Any odd function will be completely represented by its sine series, whereas every even function will be completely represented by its cosine series. And all that really tells us for our coefficients here, for an and bn, that tells us that an will always evaluate to 0 and bn will not. So we can just say that an is equal to 0, so really we're just looking for b5. Let's solve for bn. That will be 1 over L, integral from -L to L, f of x sine n pi x over L dx. But there are some things we can do here to make our lives a little bit easier. If we know that our function is just a sine series, instead of integrating like this, because we have an odd function, we can do this little optimization and actually integrate from 0 to L as long as we multiply by 2 there. This is just a symmetry property that we can take advantage of. Then what about these L's? Well, that's just the half period of our function. Since they tell us our function has a period of 2 pi, L will just be pi. And this L will cancel out with that pi, and we're just left with the sine of nx in there. Then what is this f of x? Well, that's not the entire function. You got to be careful about that. That's just going to be what this function evaluates to, our piecewise function, what it evaluates to on the interval that we're integrating over. So from 0 to pi, our function evaluates to 1. So we can replace f of x with a 1. And that's why it was nice turning this into 2 over pi integral from 0 to pi instead of 1 over pi integral from negative pi to pi, because if we integrated over that entire region, we'd actually have to split it up into two different integrals over the full interval because our piecewise function would evaluate to different things. So integrating, we have bn is equal to 2 over pi times negative 1 over n cosine nx from 0 to pi. This gives us negative 1 over n cosine of n pi. Well, what's the cosine of n pi? Well, if n is an integer, n equals 1, that's going to give us negative 1. N equals 2, that'll give us positive 1. N equals 3, that'll give us another negative 1. So that'll just keep flip-flopping between negative 1 and 1, starting with negative 1 for n equals 1, so we can just write that as negative 1 to the nth power. Then plugging in 0 for x, we just get negative 1 over n. So bn is equal to 2 over pi times 1 over n times 1 minus negative 1 to the nth power. And this is the nice way to write it. You could put a negative sign out here and change these up a little bit, but that's a little you're kind of creating a little bit more complexity than you really need with that, making more negative signs. Okay, fine. We have our bn. What can we do now? We're looking for b5. So let's just plug in 5 for n, and we should have our answer. So bn is equal to 2 over 5 pi times, well, what will this thing evaluate to? Well, for odd n, it will evaluate to 2, and for even n, it will evaluate to 0. And since 5 is odd, we will just get a 2 in here, so bn is equal to 4 over 5 pi, and c is our answer. Question 3, the Fourier series of the function f of t is equal to t squared from t between 0 and 2 of period 2 has a Fourier series found for us already. That's nice. Let's evaluate the Fourier series at t is equal to 2 to find this infinite sum, to find the value of that infinite sum. So this is a question, while it might not look like it, this is a question that if you do not graph it out, you will likely get it wrong. So let's take, not negative 5, let's take a look at what this function will look like. T squared from 0 to 2, that's giving us that kind of shape, and then they tell us it's of period 2, so it's just going to repeat that pattern, like so. Okay, what do we know about Fourier series in general? What did they do around discontinuities? Well, they're going to kind of split the difference. So our Fourier series will, as we expand that sum out infinitely, we'll get infinitely close to the actual line of our function here. But then when it encounters this discontinuity, it's only going to pass through the midpoint. And so what is the midpoint here? That's just f of t is equal to 2. So when they ask us to evaluate the Fourier series at t is equal to 2, and what will our Fourier series be trying to do at this discontinuity at t is equal to 2? Well, it's going to pass through the midpoint, which is just, yet again, f of t is equal to 2 for t is equal to 2. So let's use that fact to help us solve this. We said right away that if we plug in t is equal to 2, f of t must be 2. So I'll write that as 6 over 3 is equal to 4 over 3 plus 4 over pi squared sum from n is equal to 1 to infinity of the cosine of 2 pi t. 2n pi. And for integer n, this is always going to be a multiple of 2 pi, so that will just evaluate to 1. So we have 1 over n squared. And then for this last term, we're going to have the sine of 2n pi, which is, yet again, always a multiple of 2 pi, and so that will always evaluate that entire term to 0. So this is what our expression turns into. Let's subtract 4/3. We get 2/3 is equal to 4 over pi squared, and before I write our sum, let's just multiply this out. We get pi squared over 6 is equal to the sum from n is equal to 1 to infinity of 1 over n squared. And this should be a result that is kind of baked into your head from them talking about it in lecture. But the whole point of this question, because this test you had to show full work on, the whole point of this question was to get you to run through this process, not to be able to just remember that pi squared over 6 is our answer. Okay, that's question 3. All done. Question 4, if we write f of t is equal to cosine of t from 0 to pi over 2 as a sine series, so a function represented like that, what is b1, the first coefficient on the sine series? So yet again, first step, the first thing that comes to mind should always be to graph the thing. We have the cosine on 0 to pi over 2. There we go. And they want it as a sine series. So we have to do a little bit of work here because this is not the full period. In order to express it as a sine series, we need it to be an odd function. So we need to put extensions. We need to put an extension on this function right here. And what did we say about odd functions? Well, we said that f of t must be equal to negative f of negative t. And that will occur when we reflect our function across both axes. So I kind of have to draw it differently. But if we reflect it over the y-axis, we'll get this dashed line here. And if we reflect it over both axes, we end up across the origin. So the correct extension of our function is given right there. And we can add another period here on both ends, and you'll see we get this kind of pattern here. So what is our function? Well, this is just the cosine function. Cosine of t from 0 is less than t is less than pi. You see, we've extended it all the way up to pi, where then the function repeats itself. Okay, awesome. So let's set up our integral for bn. We know that in general, for a sine series, bn is 2 over L, integral from 0 to L, f of t, that's a terrible t, f of t sine n pi t over L. And in our case, since L will be pi over 2, right, we want the half period, and since a full period is pi, L is pi over 2. Oh my god. Okay, gotta turn my computer volume off. There we go. Since L is pi over 2, we can replace those. All of our L's, we get 4 over pi here, pi over 2 right there, and we're going to get 2 n t. And what can we replace our f of t with? Well, that's just going to be whatever our function is, whatever our f of t is, along the interval from 0 to pi over 2. And originally, we were just told that that's the cosine function. So we'll just put cosine of t in there. Now, it'll make our lives a little easier if we go replace our n's with 1's right now, since we're looking for b1. So let's just do that. And that'll give us 2t in here. They give us a nice formula as well for a generalized integral of this form. I'm sorry about the dog barking. So let's apply that. We have 4 over pi times, what do they want? Okay, the negative of some fraction minus another fraction evaluated on those original bounds, so 0 to pi over 2. Let's fill in these spots. They want the cosine of m minus nt, where m is the thing on the sine and n is the thing in the cosine. So that will give us cosine of t, and then we're just going to divide by 2 times that. Then for our second fraction, we have minus the cosine of m plus n. That'll be cosine of 3t over 6. So plugging in pi over 2 here, what do we get? Well, the cosine of pi over 2 and the cosine of 3 pi over 2 will both be 0. And then plugging in 0, we get negative 1/2 minus 1/6, which is equal to negative 2/3. So solving, I don't know why I have a pi over pi here. This should be 4. Solving, we have b1 is equal to 4 over pi times 2 over 3, which is 8 over 3 pi. And there's our answer. That's E. Question 5. A mass spring system with m is equal to 2 and k is equal to 32 is subject to an odd periodic force whose Fourier series is given here. Let's find the first non-zero term of the steady periodic solution. So let's set up our equation. In general, we have mx double prime plus kx is equal to f of t. And they tell us that m is 2 and k is 32. And let's just put our function in. Our function is approximated by the sum from n is equal to 1 to infinity of 20, 1 minus negative 1 to the nth power over n pi sine n pi t. And let's just do a couple little optimizations to make our lives easier in the future. We'll turn this into a 16 and divide that also by 2 and get 10 right there. That's perfectly legal for us to do. So now, just like kind of what we did in 266, or I believe they did some of this in 262 as well with undetermined coefficients, what we're going to do is assume that x of t is a similar kind of sine series. And what do I mean by similar kind? Well, it's probably going to have different coefficients on it, but it's going to have the same kind of sine term to it. So we'll get the sum from n is equal to 1 to infinity of some different bn times the same sine of n pi t. And we can also take the second derivative under that sum with no problem and get the sum from n is equal to 1 to infinity of negative bn n squared pi squared sine n pi t. So now what we're going to do is plug this x of t and this x double prime of t into our equation, and we'll be able to solve for bn in terms of n. So this is going to be a long one. We have the sum from n is equal to 1 to infinity of negative bn n squared pi squared. And instead of writing the sign, because we're going to cancel it out in a second, I'm just going to put a big S. Then we have plus 16 sum from n is equal to 1 to infinity of bn, and I'm not writing the sign, bns is equal to our function. The sum from n is equal to 1 to infinity of 10 times 1 minus negative 1 to the nth power over n pi s. And so it's a little sketchy to do math-wise, but what we can do, technically, whatever, is divide out our sines and our sums, because everything is being summed. We can get rid of those sums and the sine terms, and our lives will get a whole lot easier if I can just rearrange things real quick. Okay, so let's solve for bn. We can factor it out on the left side, and we'll just get bn times 16 minus n squared pi squared, so that bn is equal to 10 times 1 minus negative 1 to the nth power over n pi times 16 minus n squared pi squared. Okay, awesome. And since this was the bn that corresponds to the solution, x of t, and really this is x sp of t, the steady periodic solution, we can just plug that bn in and say that x of t is equal to the sum from n is equal to 1 to infinity of 10 times 1 minus negative 1 to the nth power over n pi 16 minus n squared pi squared sine of n pi t. Awesome. And whenever we have 1 minus negative 1 to the nth power in this final form, we can make our lives slightly easier by getting rid of it, multiplying the numerator by 2, and changing this to n odd. Because that 1 minus negative 1 to the n component will evaluate to 2 whenever n is odd and 0 otherwise. So what will the first non-zero term of our steady periodic solution be? Well, for our first odd integer n, we will get what? For n is equal to 1, we get 20 over pi times 16 minus pi squared sine of nt. And that is answer choice A. And when I say nt, I meant pi t, because that n is being replaced with a 1. Okay, that's A. Question 6. A mass spring system with m is equal to 1 and k is equal to 9 is subject to an odd periodic force of period 2k given there. For which of the following k's does pure resonance occur? So let's take a look at what our equation will look like. We have 1x double prime plus 9x is equal to f of t. And if you cast your mind back to what we learned about these systems in 266 or 262, I'm not even sure if you talked about them in 262. I don't even know. You'll remember that we can just take this function here, take this differential equation, and use the characteristic equation to figure out what this system's natural frequency will be. So that'll just be solving r squared plus 9 is equal to 0, which has solutions plus or minus 3i. So if there was no forcing function, x of t would be equal to a cosine of 3t plus b sine of 3t, like that. So what this tells us is that the natural frequency is equal to 3. And so really what we're going to try to do here in just a second is when we find the Fourier series, of this function right here, what we're looking for is for there to be a non-zero term in that Fourier series that has a frequency of 3. If we get a sine of 3t in there, and since this is an odd function, we will be using a sine series, no cosine action here. Since we're using a sine series, if we get a 3t in there, that will give us resonance. So we're just looking for the k that makes that happen for us. So let's set up our equation for the Fourier series of f of t. We'll say that f of t is approximated by the sum from n is equal to 1 to infinity of bn sine n pi t over k, because they tell us that we have that this function has period 2k, so our value for L, our half period, will just be k. Now bn, like usual for a sine series, is 2 over L, which is k, integral from 0 to k of f of t sine n pi t over k dt, where f of t on the interval from 0 to k just evaluates to 1, like they tell us right there. So we can replace that just fine. Okay, so solving for bn is equal to 2 over k times minus k over n pi cosine of n pi t over k evaluated on 0 to k. Well, if we plug in k for t, we'll just get the cosine of n pi. So that's negative k over n pi times negative 1 to the nth power. And over here, we'll just get negative k over n pi. So solving bn fully, we get 2 over k, 2k over nk pi, so we can get rid of those k's and just get 2 over n pi times 1 minus negative 1 to the nth power. And we know that this will be 0 for all even integer n's, and it will be non-zero for all odd integer n's, and that will come in handy in just a second. So since we now have bn, we can say that f of t is approximated by the sum from n is equal to 1 to infinity of 2 over n pi times 1 minus negative 1 to the nth power sine n pi t over k. And what we said a second ago, more like a couple minutes ago, is that what we're looking for is for this sine term to have, well, we want a non-zero sine 3t component, essentially. And since our bn will evaluate to some non-zero number for all odd n's, we're good, because if we plug in n equals 3 here, which is kind of all we can do to get a 3t, I need to back up a second. Sorry, I need to back up. Let's extract the coefficient on t here from inside there, because we said we're looking for that to equal 3. We have n pi over k. That looks like a k. N pi over k is equal to 3. N can only be an integer. K can only be a float. Well, it can be. It can be anything, actually. So how is this going to work? Well, if k is equal to pi and n is equal to 3, then that's going to work. That's going to work perfectly. We will just get 3 pi over pi is equal to 3. And now all we have to check is that n is equal to 3 has a non-zero term for bn out here, which it does. We're going to get 4 over 3 pi, which is perfectly fine. And because we've found a matching frequency term in the Fourier series of our forcing function, we will get resonance. We'll get pure resonance with this system. So that is k is equal to pi. That gives us pure resonance. Sorry, that was a little botched there at the end. I hope that made sense to you. And that's actually going to be the end of this, because then they get off into partial differential equation stuff, which, you know, I could go do that right now. I don't think it would be particularly helpful. I'm going to put more time into going over more sine series and cosine series questions from other semesters, from quizzes that Chen gave, and from the final exam, the kind of second third of that. And if you're looking for more of an in-depth dive into Laplace transforms, inverse Laplace transforms, and Laplace initial value problems, I have dedicated videos for all three of those from 266, where we covered exactly the same topics that we've been talking about. So that's 7.1 through 7.6 from the textbook. And you can just, you can go find those. Hopefully I'll remember to add them to my playlists for MA303. But I hope this was helpful for you. I really do like the way that Chen tests these topics, where he doesn't actually make us do any crappy integration like my lab math does. That's the thing I'm scared about for my midterm, when I take midterm 2 in about, 48 hours, because really the focus of this part of the course isn't can you do like crappy integration by parts. This question right here, if they made us find the Fourier series of t squared, you'd have to do integration by parts twice, like nested inside each other. Oh, that's gonna suck. I don't even get me started on how my lab math testing is ruining like Purdue math. Okay, whatever. Hopefully this was helpful, and go check out those Laplace transform videos if you need some more help or tips or guidance on that.